Yay!
Yay! All right, next up is the idea of the cross product or vector product, although it's a little ambiguous because the dot product, I suppose, is a vector product. But the idea is that when we do the following thing, when we do a cross product, what we get out of it is a vector. And it looks something like this. If I have vectors A and B, any two vectors A and B, they're going to define some sort of a plane that includes them. So using the cross product, which we'll do in just a minute, you can always find a vector normal to that plane, perpendicular to that plane. In physics, it turns out that is a crazy useful thing to do. So that'll be the focus of this little problem, is to figure out what is the vector normal to that little triangle. Just imagine it's a whole plane, but we want the vector normal to that triangle. Okay, first of all, let's define what the cross product is. You've probably seen it before. Going back to what we did before, if I have a vector A and a vector B, one thing I could do is I could figure out how much of A is going in B's direction, if there's an angle theta between them. And then I could figure out the thing called the dot product. This is A cosine B, right? So the dot product, A dot B, we said was AB cosine theta. It's how much of A is going in B's direction and then multiplying those things together. Well, sometimes that's useful. If A is like the wind and then B is the direction that something is moving, it turns out that finding how much of the wind is contributing to the movement in that direction gives you something called the energy, and we'll be doing that later on. Just in physics, it turns out that's useful to figure out how much of one vector is in the direction of another vector. But sometimes you don't want to know that. Sometimes what's useful is the perpendicular piece. Right? This is A cosine theta. That's the part that's going in the direction of B. Sometimes it's useful to find that bit, the perpendicular part, what the perpendicular part of A with respect to B is. And this is just the other trig function, right? This, oh, maybe that went off the side. This is, oops. This is A sine theta, right? The perpendicular bit would be A sine theta. Sometimes we want that. So we define another thing with another multiplication symbol. And we just call it the cross product. And the cross product is going to involve the perpendicular bit, AB sine theta, measuring how perpendicular two vectors are. Except there's one more little piece. It turns out it's useful that what we get out of this is a vector and not a number. So this is the magnitude of the cross product. The direction of the cross product is going to be normal. It's going to be perpendicular to those two vectors. If I just draw a simple XYZ, and if this is A, and that's B, right? A cross B, so A and B are in the XY plane. A cross B is going to be perpendicular to both A and B. Well, if you look at that, you can imagine there's two vectors perpendicular to A and B. Here's one. Points that way in the Z direction, right? But there's another one in the minus Z direction. So it's ambiguous. Which one are we talking about? There's two vectors perpendicular to that plane. We want that one, just by convention. And the way that we do it is called the right-hand rule. You might have been taught this in lots of different guises. What I always do is I just take, let me get my hand in the camera, I just take my fingers in the direction of the first thing, like the X, I twist it in the direction of Y, and then my thumb is pointing in the Z. That's just called the right-hand rule. And that's, by convention, we know which perpendicular vector we're talking about. Okay. Also, by the way, this is kind of a neat thing. Notice that A, B sine theta, that's measuring this. Geometrically, that represents the area swept out by A and B. That's kind of neat. So it has sort of a geometric interpretation. Okay, so if you know A and B, the lengths and the angle between the vectors, you can get the cross product. It's easy. What if I know the components, though? That's a little bit tougher. Remember, for the dot product, we had A dot B was ax bx plus ay by plus az bz, right? You multiply the components and add them together. For the cross product, you're out of luck. It's more difficult. Now, you might have been shown along the way a way to get the cross product that involves the determinant of a 3x3 matrix for some reason, right? Nobody ever probably tells you why it's the determinant, why a matrix has anything to do with this. And then it's difficult to do because you got to remember that middle column of the matrix gets a minus sign, and you got to remember which direction the determinants go. It's prone to error. You're bound to miss a sign in there sooner or later. So I'll show you a little shortcut. This is what I do. I never memorize the cross product in components because I'll never convince myself that I haven't remembered it wrong. So instead of memorizing it, what I do is I generate it, and I generate it like this. All you have to do is just draw a little cycle, x to y to z and back to x. I just draw a little wheel, and I can generate the cross products like this. A cross B it's a vector, right? It's a vector product. And what is the x component of the vector? What you do is you just go around the wheel. If I want the x component of the vector, I just imagine going around the wheel in this sense. So the x component just gets me in order, a, y, b, z, and then I subtract off the reverse, a, z, b, y. Cool. If I want the y component of the cross product, I start out with y, and I just go around the cycle. So it's a, z, b, x, and then I subtract off the reverse. Oops. ax, b, z. And then if I want the z component, it's ax, by minus ay, bx. Cool. So this way, if you just practice it a couple of times, this way you never need to remember or memorize the cross product. You just generate it whenever you need it, component by component. It's just going around that little wheel, and that little wheel is a heck of a lot easier for me to remember than remembering all those components and what the order is for each of those things. Okay, so we have the recipe for the cross product. All that's left is to actually compute the thing. The way that I have it written up there, it looks like, what is my vector A? This is sort of like what we did last time. How do I get from the beginning to the end of A? Let's see. The beginning of A is at x coordinate 2. So to get over there on the y-axis, it looks like I have to go minus 2 in the x direction. And it looks like I have to go 1, 2, 3 in the y direction, and I don't do anything in the z, so I leave that alone. What about vector B? How do I get from the beginning to the end of B? B starts on the y-axis, so it looks like in the x, I don't do anything at all. In the y, I got to come back 3 minus 3 in the y direction. And then what do I do in z? I go up 1. Okay. So the vector is just sort of like a recipe. It's directions for getting to the beginning, from the beginning to the end. Okay, so I've got A and B, so I'm ready. Let's do the cross product. And I'm just going to do exactly what it tells me. A cross B is equal to, all right, A, Y, B, Z, that looks like 3, minus A, Z, B, Y. Oh, I messed that up. A, Y, B, Z, hold on. I see. Okay, A, Y, B, Z. A, Y, B, Z is 3. A, Z, B, Y, 0. Okay, I had it right. 3. And then I got minus. A, Z, B, Y is 0. Cool. Next, AZBX, 0, minus AXBZ, minus 2. So that's going to make that a plus 2. Cool. Last, AXBY, that's going to be a 6, minus AYBX, 0. So it looks like my vector is going to be 3, 2, 6. So that vector is going to be normal to the plane. That's the vector of that little triangle, normal to that little triangle. Sometimes what we want is the unit vector in computer graphics. Often we want the unit normal so that it has a length of 1. How do I make the unit vector? Remember the definition of any unit vector R is just the vector, and then what do you do with it? You divide by its own length. If you divide a vector by its own length, it's just obviously going to have a length of 1. That's what we want. So just take a vector, divide it by its own length, and that's the unit vector. So take this thing, 3, 2, 6, and divide it by its own length. All right, what is the length of that vector? Square root of x squared plus y squared plus z squared. So let's see, it's going to be 36 plus 4. That's going to be 49. Square root of 49 is 7. So the unit vector is going to be 3/7, 2/7, and 6/7. Whatever those fractions turn out to be. Let's see, that's going to be like, 0.42, 0.28, 0.8, 6? I don't know. Something like that. And whenever you get a unit vector, just take a second and verify. If I take these things and take x squared plus y squared plus z squared, I should get approximately 1, right? So that's the unit vector that points in the same direction. So this is the normal vector n, and then this would be n hat. That's the unit vector that points in the same direction as the normal vector, but it's just got a length of 1. Very, very cool. All right, so next time we'll move on to a brand new unit, kinematics, because now we know everything about vectors.